That's your assignment. Or it doesn't have to be intelligent. But okay, let's see, is the time yet? Another few seconds. I see I lost some attendees when I made that requirement. Did I don't know. Okay. All right, so let's start. Our first speaker in today's session is Nicholas Cazet from UC Davis. Take it away, Nicholas.
All right, thank you for having me. Thank you for organizing. I am coming from UC Davis. I'm a student of Jennifer Schulten's there, and I'm going to talk about the triple point number of surface lengths. And one of the primary tools used for those that I've used is Quandles. So to just say what a quandle is first, it's, let's see if I can do a better. Yeah, okay, there we go. So a quandle is this algebraic set that has this operation, and it looks terrible. But in fact, these three axioms are related to the Reidemeister moves, and it's how they're defined. So if you know three coloring or Fox's n coloring of a knot, these are the axioms that satisfy those relations. And three coloring of a knot doesn't depend on the orientation, and that is a specific quandle that's called a key. But a quandle is going to be something that colors the arcs of a knot, or in our case, a surface knot, and it takes in and it needs an orientation. So that's the generalization from a key, which is like a three coloring that doesn't. I guess just to convince you maybe of the first one, if I had a Reidemeister one move, and coloring is the same as just assigning an element to the arcs. So if I assign this the x and this an x, it would be the same as the endpoints having an x together. So this, as I cross over a crossing, I do this multiplication, which would be x times x. And then to have the endpoints be equal, x times x should equal x. And then the second corresponds to a Reidemeister 2 move, and a third is going to be a Reidemeister 3. And they actually correspond to what will be Roseman moves for a surface length diagram. One example is this Fox's n coloring. This is a dihedral quandle. It's really a key. It doesn't depend on the orientation. So three coloring satisfies this relationship of 2y minus x mod n. So for some n. And one way that they're not all nice like this, but this one has kind of a fun interpretation geometrically. You take a regular n-gon, and to describe the product, to create a multiplication table, say you're doing 5 times 4. The 4 is going to be a straight line that goes through the center and the number that's in the second entry of the multiplication, and then the first reflects across that line. So 5 times 4, you reflect 5 across the 4 line and you get 3. And this describes how you would color actually. So you have the over strand, the under. So this would be a 5, this would be a 4, this would be a 3. And you would maybe give it an orientation that tells you which way. But the key doesn't matter the orientation. So it should be the same if the arrow was going the other way. So, okay. So a surface link is a smoothly embedded closed surface in 4 space. And the knot theory, the length theory of this is that you up to ambient isotopy, or up to smooth isotopy. If your link is just diffeomorphic to S2, it's called a 2 knot. So Sn into Sn plus 2 is just called an n knot. And you would say that a surface link is trivial if each component bounds a handle body that's disjoint from the other. And perhaps if it's a non-orientable surface with some genus, that you would say that at least one of the handles is attached inconsistently to give it a non-orientable property. So for the non-orientable case, you would say for the RP2 that there's two standardly embedded RP2s that give you a diagram that looks like the cross caps, and it depends on the normal Euler numbers that tells you the two distinct classes of those. And then from there and up, if it bounds this non-orientable handle body. And then a surface knot will just mean that it's connected. So what you can do is, just like in knot theory, you have a knot in 3 space and you can project it down to 2 space generically and give it crossings. So for a surface, you would have it in 4 space and you project it down to a hyperplane in 3 space. So that would generically give you not necessarily an immersed surface, because you can't have these branch points, but it will give you this generic surface in 3 space. And the singularities I'll show you in the next section, but you would, along the singularity, the singular set, you give it crossing information just like you do for a knot diagram. So for a knot diagram, the singular set are just double points. You give it over under information. For this, you would also give it crossing information, but now you have sheets, so you would call it a broken sheet diagram. So you break it like you would break a crossing. So locally, you have these 3 singularities where you would see a lot of these double point curves. So where these 2 sheets intersect, and then possibly these double point curves intersect where at triple points. And you may have branch points where the double point curves end on their own. So a singular set might look something like this. So instead of having crossings, you would have this graph that has maybe 6 valent points corresponding to the triple points, or 1 valent points in the graph vertices that correspond to the branch points. So in this sense, you can create a diagram for a surface link, but as you can imagine, it's very easy to create one that's too hard to visualize, where you could have a sheet that kind of wraps around and everything that you care about is hidden. So it is kind of hard to visualize. A nice way to see it is this singular set where you're looking at the graph. Just like knot theory, there are moves on diagrams that tell you if you have 2 broken sheet diagrams that represent the same surface length, they're equivalent up to they're Roseman moves. So just like a Reidemeister move, they do encode. Some of these look like just the 2-dimensional case of a Reidemeister move. Like this first one, if I were to take some cross sections in the middle, the cross sections would end up looking like what's happening in a Reidemeister 1. Let's see, this one would be a Reidemeister 2 kind of equivalent if I took some cross sections, and then this one would be the 3 case. And then there's some other just sort of foundational things, like saddles are essentially very important, Morse theory, decomposition, there's either maximum, minimum saddles. So to consider what happens with the sheet passing over a saddle is important. And then the bottom right one's kind of hard to see, but you have a triple point and then you have a plane that's passing through, and it's called a tetrahedral move. But there is a combinatorial way that you can approach this, just like knot theory. And the question that I had been studying is the triple point number. So just like the crossing number for a knot, how few crossings do you need in any knot diagram that represents that class? You have the same thing for the surface link, where instead you talk about its triple point number. So the triple points are a discrete set. The double points come on curves, and then the branch points are also discrete. So since it's compact, you ask, how few triple points can you have? And you always have a finite amount of them. Turns out it's very hard to say much about the triple point number, because there's weird things that can happen. So this is a very impressive list of results, but you can kind of imagine and compare it to the not case that it's a lot slower paced than what would be said about knot theory. It's quite easy to say a knot, there's no knot class with a crossing number of 1, but here it kind of took a significant paper to say that for a surface link, you can't have a triple point number of 1. So if you see just one triple point, there is some Roseman move sequence that will eliminate that. It was later shown, this is all Sato and Shima, but it was later shown that you can have your triple point number go off to infinity, that there's a family that has that property. The 2 twist spun trefoil, the twist spin is kind of maybe it's a little political, but I think it's kind of the simplest surface knot that you could, non-trivial surface knot are these twist spins. So I have a tangle representing the trefoil in 3 space, and then I spin it around in 4 space. And if I do it correctly, it'll give me a sphere that's knotted. And potentially as I go, it just spinning gives me something that has no triple points. So as I'm spinning, I can also twist this, and that will give me some triple points. So the 1 twist spin is actually of a knot is actually always trivial. So the 2 twist spun is kind of the first non-trivial idea that you could have, and it's generally what you would consider for first. So that was shown to have a triple point number of 4 for the trefoil and 3 or 6 for the 3 twist spun, and that uses quandles. So it uses this kind of combinatorial approach that exhausts. If you have 3 triple points, this quandle can only give a result of 0, whatever that means. And so because it has a non-zero quandle invariant, it must have at least 4. But the interesting thing that was shown is that the triple point is not additive. It's not known for knots, but it's not additive for surface knots, because there's this idea that you can have a knotted 2 sphere and you connect summit with a projective plane, and then it unknots and it turns into a projective plane. So there's this very odd, there's odd properties when you can be non-orientable. And one of them means that you cannot be additive under connect sum for the triple point number. It was later shown that was expanded, the result of being able to combinatorial prove that you only have so many triple points. It was later able to go up to 8, but because of how cumbersome and how many cases you can check, that method kind of is running dry. It was later shown that no orientable surface knot has a triple point number of 2, and if you're a genus 1 surface knot, you must have at least 4 triple points. And that's kind of the girth of the triple point problem. I had specifically been considering the idea of, can you have a family of surface links and have their triple point number go off to infinity? So this first result by Kamada in 93 was kind of the first of that kind. And it said that if you're considering 2 knots, so knotted spheres, that you can find a family, the twist spins of something, that the more you twist, it goes off to infinity. So you can find a 2 knot whose triple point number gets arbitrarily large. And that's a great result. But in the landscape of surface links, now there's not just an S1 component you can have for a link. There's, any genus and non-orientable or orientable. So can they all satisfy that in terms of that classification? Like if I had genus, can I have this property of going off to infinity and their triple point number? If I have 3 components or 4 or n components, can I also have that result? So that was kind of what I was considering for my project. And there were some results that expanded this. So for any positive entry, and there's a 2 component that has 2 component surface link with this property. So one is trivial. They're both trivial and non-orientable, and you can pick their genus, but could you increase the number of components here? And later Oshiro showed that you can have one component be a torus and then the other have even genus as long as it's non-orientable. And There's another result that she showed that you can have two components and both of them, you can pick the non-orientable genus of them. And you have this property that you can always find one in this family whose triple point number is as large as you want. So what I showed was that you can kind of pick and choose a lot of kind of what I was saying. Like you can have k plus m plus 1 components. You can pick the k and the m, and they're all trivial components here. They all bound handle bodies disjoint from each other. And you also get to pick the genus. You can pick the genus as however you'd like for the orientable case, and for the non-orientable case, you have to restrict to being even. But this gives you a surface link whose triple point number is calculated and depends on the genus of the non-orientable components, and you can let that go to infinity. So this shows that you can kind of have as many components as you want in this non-split surface link, and you still have that property. So to prove this, it used Quandles, but it actually used a generalization of Quandles. So generalizing a generalization, and it's called a symmetric quandle. So this is this family here. The idea is there's kind of a lot to explain with this picture, but I can color things. So generally the quandle needs an orientation for the surface link, but what do I do when it's not orientable? Well, there's this thing called a symmetric quandle where each sheet of that broken sheet diagram I explained can give it its own orientation. So symmetric quandle works with local orientations of each component of the sheet. So each component can always be oriented. So it's called a motion picture. So this is like a Morse decomposition, and I'm taking cross sections as I go up the surface link. The grays bands are bands, so they correspond to the saddles. The coloring of the link diagram, I truly want to color a broken sheet diagram, but if I had a broken sheet diagram of this, we couldn't see where the triple points are going to be in here. So what I'm going to do is I have a broken sheet diagram, and I'm going to cut it up Morse theoretically and get a bunch of link diagrams. So what you imagine here is that you have, and the colorings of the link diagrams, I do have a slide explaining this, are going to correspond to colorings of the sheets that you get. So actually, let me take one moment to go back here. I forgot to do this. So to color a link broken sheet diagram, a surface link, what you do is you give the sheets a color, just how you would color a knot, where you can actually just look at the spine of it. Maybe I should just do that. So like you would color a knot, you can color these broken sheets kind of just along their spine. So I give a sheet a color, and then along a double point curve, I have this product that I play into, and I get to run across that. So I'll just briefly show you this. So there's a lot of saddles and a lot of interesting things going on here and colors, and it looks pretty cool. So what's going on here is that as I go from slide to slide, if there's no band, if there's no critical point, the link type stays the same. So I can go through this decomposition with a sequence of Reidemeister moves. And if I see a Reidemeister 3 move, what I see is this right picture, and it corresponds to a surface that's this generic surface creating a triple point. And on the left, it'll correspond to a Reidemeister 1, will correspond to a branch point. So you imagine you take these cross sections as I go, and I see this, what's called a motion picture. And this was that previous slide, what we were seeing there. So that truly is creating a broken sheet diagram that I'm going to analyze. And if I color, so these letters are representing the colors. If I color the link diagrams as I go, the sheets that it traces out in the motion picture are going to be colored the same as the arc that represents it in the cross section. So there's a way, so you color the link, this colors the broken sheet diagram, you can interpret and get all the information from the broken sheet diagram by looking at the colored link diagram like I showed you in that picture. So here's a nice picture that shows what it would look like if you could see it. So this corresponds to this spinning of the trefoil to get a twist spun, or this is truly just starting to spin. So maybe it's just the 0 twist spun. But I can color the link, or I could color the knot diagram, and that's going to tell me how to color the sheets I create as I go. And the top twisty thing at the top is the singular set of this two sphere that I'm going to get by spinning the trefoil and twisting it as I go. And then I'm going to cut away all of the gray parts, and I'll see just the local picture that I assign the colors. And then the beginning and the end of this connects up, and that creates the singular set of a twist spin. Okay, I'm at the 20-minute. I just super briefly, I'm going to just say one other thing that I worked on is that there is this, there's this table that was generated to try to enumerate links based kind of on like a crossing number. And it's a well-known Yoshikawa famous table. And generally these are the surface links you'd like to start to look at. This idea is that if you had a self-indexing Morse function, you take the one critical level that has all of the bands on it, and you ask how few crossings and bands, or an immersed link diagram that corresponds to the saddles, how few crossings plus those immersed double points do you need in any diagram that represents that critical middle section. And that's called the CH index, and that's this big number 2, 2, 9, 10. So the final thing that I did is I went through here and tried to either calculate or bound the triple point number of those well-known surface links. And most of them have a triple point number of 0. And these ones right here were previously calculated. So this corresponds to the 2 twist spun trefoil, although it's called something different here. So some of these already had a well-known number, and then I created these bounds for the ones that were not. All right, that's all I have. I'll leave it on this nice, cool, fun picture.
Let's thank the speaker, and you can unmute and clap, or is there another way to do it? But and then I was going to ask, does anyone have questions they'd like to ask? Yeah, you suggested a couple things you said, suggested questions to me based on what little I know about knot theory. And so is there a notion for an embedded surface and force space of an unknot when it's unknotted?
Yeah. So that would be when it bounds a handle body. So there's a couple ways to do that. So you could say the surface link, each component bounds a handle body in the force space that's disjoint from the other. It also, an equivalent way is that the surface can be isotoped into a 3-space hyperplane. So if you can actually see it in 3 space, then that's another way to say that it's unknotted.
Are those equivalent?
Yes. But it's not known if your fundamental group is Z, if that's unknotted yet. It's a conjecture, but that would be a pretty famous good result if you could show that.
I had one other question. So can you connect some knots and get an unknot? In other words, do knots have inverses?
Yeah, well, I don't imagine it. I guess I can't say for sure. I don't know if it's known for sure if some knots have an inverse, but there is that weird case where you have a knotted 2-sphere and you can connect some with an unknotted RP2.
Yeah.
And then that somehow it unknots the two sphere. So there is this weird sense that there some can be trivialized through a connect sum, which is unlike normal classical knot theory. But I would probably say that if you're stuck to being orientable, that probably doesn't happen. But there's not a proof yet that that's the case.
Yeah. Other questions? Okay, well,
All right.
I'm going to thank this. Let's thank the speaker one more time.